Last week, Jean present Schweinsberg from UCSD. I'm going to discuss branching Brownian motion with absorption.
Okay, thank you, and thanks to the organizers for the opportunity to speak here. I'm going to talk about some Yaglom-type limit theorems for branching Brownian motion with absorption. This is joint work with Julian Beresticki, Nathaniel Beresticki, and Pascal Maillard. The new results that I'm presenting here are based on work in progress with Julian and Pascal, but many of the tools that we're using originated in earlier joint work with both Berestickis. So let me begin by defining branching Brownian motion with absorption. We begin with some configuration of particles to the right of the origin. Each particle independently moves according to standard one-dimensional Brownian motion with a drift to the left of mu. And for simplicity, we're going to say that each particle splits into two particles at rate 1/2, although our results can be extended to handle more general supercritical offspring distributions. And then particles are killed if they reach the origin. So here's a picture of the process. We begin with just this one particle at time 0. This particle moves according to one-dimensional Brownian motion with drift for an exponentially distributed time with rate 1/2, and then it divides into two particles. And then those two particles independently move according to Brownian motion with drift until they divide, and so on. And here you see we have these two particles that hit the origin and were killed, but we also have these three particles that are still alive at time t. Now, before we move on, I want to say something about the motivation for studying this process. My primary source of motivation comes from the fact that branching Brownian motion with absorption has been proposed as a model of a population undergoing natural selection. And this goes back to some earlier work of Brunet, Derrida, Mueller, and Meunier. In this setting, particles represent individuals in a population. The position of a particle corresponds to the fitness of the individual. Branching events, of course, represent births, and absorption at 0 models the deaths of individuals whose fitness gets too low. Particles move over time because the fitness of individuals changes from one generation to the next. Now, there's also some motivation coming from partial differential equations. It turns out that the position of the rightmost particle in branching Brownian motion is very closely related to a partial differential equation known as the FKPP equation. This goes back to some early work of McKean. And later on, Harris and Cipriano used branching Brownian motion with absorption to study a one-sided traveling wave equation that's closely related to the FKPP equation. And finally, I want to mention that some of the tools and heuristics that have been developed for branching Brownian motion have also been used to study the extremes of various other stochastic processes, including the two-dimensional discrete Gaussian free field, two-dimensional cover times, and also a more general class of log-correlated Gaussian fields. So probably the most basic question that one can ask for branching Brownian motion with absorption is whether the process goes extinct or whether some particles survive forever. And this question was answered in Harry Keston's original paper on branching Brownian motion with absorption from 40 years ago. And Keston showed that if the drift to the left is greater than or equal to 1, so that particles are being sent fairly rapidly towards the origin, then with probability 1, the process goes extinct. On the other hand, if the drift to the left is strictly less than 1, then with positive probability, there are particles that survive forever. For the rest of this talk, we're always going to assume that mu is equal to 1, so that we're in the case of critical drift. And we're going to be interested primarily in two questions. First, we know that this process is eventually going to go extinct, but what is the probability that the process survives for an unusually large time t? And then second, conditional on the event that the process survives for an unusually large time t, what can we say about the configuration of particles that are still alive at time t? And results like this are known as Yaglom-type limit theorems, after the result of Yaglom pertaining to critical Galton-Watson processes conditioned to survive for n generations. So now I'm just going to jump right into stating what I consider to be the main results, although I will state sharper versions of these results as well as some other results later on. So we're going to let n of t be the number of particles in the system at time t, and zeta will denote the extinction time, and I'm also going to let c be this constant 3 pi squared over 2 to the 1/3 power, which is going to keep coming up. Now in 1978, Keston showed that if we start the branching Brownian motion from a single particle at x, then for sufficiently large t, the probability that the process survives for at least time t is bounded above and below by these two quantities. So basically the survival probability until time t looks a lot like x times e to the power x minus ct to the 1/3 power, but notice that here the upper and lower bounds differ by more than a constant factor because of these e to the plus or minus k log t squared terms that show up. So here is the new result, which is sharper. So here and throughout the talk, BMS refers to Julian Barosticki, Pascal Maillard, and myself. And this result says that if we start the branching Brownian motion with a single particle at x, then the probability that the process survives for at least time t is asymptotically equivalent to a constant times x times e to the power x minus ct to the 1/3 power, where this symbol here means that the ratio of the two sides is tending to 1 as t tends to infinity. So I should mention that Derrida and Simon obtained this result more than a decade earlier using non-rigorous methods. And also, in joint work with Julian and Nathaniel Barosticki, we obtained upper and lower bounds on this survival probability that were correct up to multiplicative constants.
What was the method of Derrida and Simon?
I'm not familiar with their specific method, but they did have the result back in 2007. Now, we also have a Yaglom-type result for the process conditioned on survival for a large time t. So again, n of t is the number of particles at time t, and r of t is the position of the rightmost particle at time t. That is the particle that's furthest away from the origin. So in 1978, Keston showed that, again, if we start the process from a single particle at x, and we condition on the event that the process survives for a large time t, then the probability that the number of particles at time t is larger than e to the k1 times t ninths log t to the 2/3 power, that's tending to 0 as t goes to infinity. And also Keston showed that it's asymptotically unlikely that there is any particle more than k2 times t to the 2/9 times log t to the 2/3 away from the origin. So we've been able to prove a sharper result here, which shows that these log t to the 2/3 factors are unnecessary. In fact, both the log of the number of particles at time t and the position of the rightmost particle at time t are of the order t to the 2/9 power. More precisely, if we start with one particle at x, then conditioned on survival until time t, both t to the minus 2/9 times the log of the number of particles at time t, and t to the minus 2/9 times the position of the rightmost particle at time t are converging in distribution to the cube root of an exponential random variable. So those are the main results. What I want to do now is to describe some of the tools that we're able to use in proving these results, which allow us to get a very precise understanding of how the process behaves. And a natural place to start is with moment calculations. We'd like to be able to calculate the expected number of particles alive at a given time, or the expected number of particles in a particular set at a given time. And it turns out there are some standard tools available to make these kinds of calculations. So let's start for the moment with just a single Brownian particle at x with a drift of -1 and absorption at the origin. And then there's a formula for the density of the position of the particle at time t, where density is in quotes because the integral of this expression is strictly less than 1, since the particle may be absorbed at 0 before time t. So this first term is simply the density of a Brownian particle run for time t. Then there's a term that we subtract because of the absorption at 0. That can be calculated using the reflection principle. And then we have this Gersonov factor to account for the drift of -1. So now let's add branching at rate 1/2 back into the process so that there can be more than one particle around at a time. And we'll let x1 of t, x2 of t, and so on be the positions of the particles at time t. And then we'll let q sub t of x comma y be e to the t over 2 times pt of x comma y. And qt is going to play the role of the density for this process when branching is included. Because if we just had a standard branching process in which each individual gave birth at rate 1/2, then the expected number of particles alive at time t would be e to the t over 2. So this result here is known as the many-to-one lemma. So on the left-hand side, so we're starting with a single particle at x, and then we are summing up the values of the function f at the positions of the particles at time t. And then this equals the integral of f of y times qt of xy. And so the idea here is that we are able to calculate expectations of various Brownian functionals by making these density calculations that involve just a single Brownian particle. And that's why this result is known as the many-to-one lemma. And in particular, if we take f to be the indicator of some set A, then what we get on the left-hand side here is the expected number of particles at time t that are in the set A. So we can calculate first moments of such quantities. Now we're also able to calculate second moments by similar methods. So this technique goes back to this early work on branching Markov processes of Ikeda, Nagasawa, and Watanabe. So when we expand out this square here, we get a sum over pairs of particles. And to have particles at the locations y1 and y2 at time t, there needs to be a branching event at some earlier time s where the trajectories of those two particles split into two. And so then some particle has to go from the position x of the initial particle to some location z in time s. A particle has to go from z to y1 in time t minus s. And the other particle created at the time of that branching event has to go from z to y2 in time t minus s. And so when we integrate this over the time s of the branching, the position z of the branching, and the positions y1 and y2 of the two particles, we get the second moment of this quantity, which allows us to control the fluctuations of the process. So it's valuable to be able to do these moment calculations. However, a complication that arises is that the moments don't actually capture the typical behavior of the process. For example, the expected number of particles alive at time t is dominated by rare events in which one particle moves unusually far to the right, and then a very large number of descendants of that particle are able to survive because they're able to avoid being killed at the barrier at 0. And consequently, the expected number of particles at time t is much larger than the number of particles at time t in a typical realization of the process. So to understand the more typical behavior of the process, we need to do some sort of truncation. We need to kill, not only do we need to kill particles at 0, but we also need to kill particles that drift too far to the right. And then after we do that, we can calculate first and second moments in the same way, provided that we adjust the density formula appropriately to account for the truncation. Now, one way of doing this truncation is to fix some positive number L and then kill particles both at 0 and also at L. And this leads us to branching Brownian motion in a strip. So let's start with just a single Brownian particle killed both at 0 and at L. And so if this particle starts at x, then there's a well-known formula for the density of the position of the particle at time t, and it's given by this expression here involving an infinite sum. And so then to calculate the density for our process, in which we also have branching and a drift, we just multiply by a Gersonov term to account for the drift, and then invoking the many-to-one lemma, we multiply by e to the t over 2 to account for the branching. And so here, by density, as before, what I mean is that if A is a subset of the interval from 0 to L, then the expected number of particles in this set at time t is given by integrating this density qt L of xy over the set A. Now, if t is much larger than L squared, the first term is going to dominate this sum. So we can approximate this infinite sum by its leading term to get this approximate expression for qt L of xy. And there are two things to notice about this expression. The first is that the expression is proportional to e to the x times the sine of pi x over L. And so this is telling us that if we start with a particle at the location x, then the number of descendants of this particle a long time into the future is going to be roughly proportional to e to the x times the sine of pi x over L. And the other thing to notice is that this formula is proportional to e to the minus y times the sine of pi y over L. And so that's telling us that once this process has run for long enough, that the particles have settled down into a kind of stable equilibrium type configuration, the configuration of particles is such that the number of particles very close to y is roughly proportional to e to the y times the sine of pi y over L. Now it turns out that we do not get sharp enough truncated moment bounds by killing particles at some fixed level L. What happens is that the number of particles in the system is decreasing over time as the process heads towards the inevitable extinction, and as a result of that, we need to allow the right boundary at which we kill particles to move closer to the origin over time. So, given a positive time t, we'll let L sub t of s be c times t minus s to the 1/3 power, where c is this constant that we had before. And now we want to consider a version of branching Brownian motion in which at time s, a particle is killed if it reaches either 0 or Lt of s. And in fact, the process with killing at this particular right boundary was already considered in Keston's original paper. So the way we want to think about this is that we choose t to be roughly the amount of time that we expect that the process can survive, given what we know about the initial configuration of particles. And then the motivation for this choice of Lt of s is that roughly a particle at time s needs to be fairly close to Lt of s in order to have a fairly good chance that a descendant of that particle will still be alive past time t. Now, of course, it's harder to calculate densities when the right boundary is moving. However, some techniques in this paper by Matt Roberts, which build on some earlier work of Novikov, allow us to get approximate formulas for the density, which in turn allow us to get approximate formulas for first and second moments. And it turns out that because our right boundary is actually moving very slowly, the formulas for the density resemble very much the formulas for the density in branching Brownian motion in a strip, except that we have Lt of s everywhere in place of L. Now, unfortunately, even when we kill particles at this curved right boundary, we still don't quite get moment bounds that are sharp enough for our purposes. And there are really two problems that remain. So, first of all, for the kinds of initial conditions that we need to consider, the variance of the number of particles at time t turns out to be the same order of magnitude as the square of the expectation. So that's not quite good enough to get a concentration result for the behavior of the particles that stay below the right boundary. And secondly, we are not able to show that the number of particles killed at the right boundary tends to 0. In fact, the best we can do is to say that the expected number of particles killed at the right boundary is bounded above by a constant. So even in a typical realization of the process, this right boundary, this killing at the right boundary, is influencing the behavior of the process. So it's natural to think about what happens if we move the boundary by a little bit. So let's say instead of killing particles at LT of S, we kill particles at LT of S plus A. Well, as we let A go to minus infinity, the variance of the number of particles at time t gets small relative to the square of the expectation. So we are able to get good control over the particles that stay below the right boundary. They start to behave approximately deterministically. On the other hand, the number of particles killed at the right boundary goes to infinity. If we let A tend to plus infinity, then the number of particles killed at the right boundary does go to 0. However, the variance of the number of particles at time t gets large relative to the square of the mean, and so we're not really able to control the particles that stay below the right boundary. So we're able to solve either one of the two problems, but we're not able to solve them both at the same time by using these truncation methods. And so what we need is another idea to allow us to understand the behavior of the process more fully. And what we're going to do is to choose the first option here. We're going to stop particles when they reach LT of S minus A, where A is some large constant. And so that will give us good control over the behavior of the particles that avoid the right boundary. But then when a particle hits the right boundary, instead of killing that particle, we're going to follow the descendants of that particle along until those descendant particles reach LT of S minus A minus Y, where Y is some other large constant. And then after that point, we're going to take those descendant particles and reincorporate them back into the process. Now, to carry out this method, we have to have a good understanding of how the particles behave after they reach the right boundary. And the analysis of these particles depends on a certain continuous time branching process, which was first studied in connection with branching Brownian motion by Neveu. So let's consider branching Brownian motion with a drift of -1, started with a single particle at, we'll just say L. And then after that process has been constructed, one can determine for every value of y, if we killed particles when they reached L minus y, how many particles would have been killed? And we'll call that number m of y. And it's not hard to show that this process that we get by varying y is a continuous time branching process. Because conditional on the number of particles that reach L minus x, each of the m of x particles that reaches L minus x independently produces a certain number of descendant particles that reach L minus x plus y. And by the spatial homogeneity, the number of such descendants produced by a given particle has the same distribution as m of y. And that's exactly the branching property. Now, it turns out that the offspring distribution for this branching process has finite mean, but is not in the L log L class. Nevertheless, as guaranteed by the Sennett to Heide theorem, there is a scaling under which we get a non-trivial limit, and Neveu showed that as y tends to infinity, y times e to the minus y times m of y is converging almost surely to some limiting random variable w. And then we have this result about the tail behavior of w, which tells us that the probability that w is greater than x is asymptotically behaving like 1 over x as x tends to infinity. So now we're ready to start to try to put these observations together into a theorem. So recall that we're considering branching Brownian motion with drift at rate -1, branching at rate 1/2, and absorption at 0. N of s is the number of particles at time s, and x1 of s, x2 of s, and so on are the positions of the particles at time s. Now, if we fix any positive time t, then for any number s between 0 and t, we can define this quantity which I'm going to call z sub t of s. which turns out to be a very good measure of the size of the process at time s. So notice that what we're doing here is we're summing over the particles at time s, and the contribution to this sum of a particle at the location x is proportional to e to the x times the sine of pi x over Lt of s. And so recall from our formula for the density of branching Brownian motion in a strip that that expression, e to the x times the sine of pi x over Lt of s, is roughly proportional to the number of descendants of that particle that are going to be around at future times. And so that's why that's giving us a good measure of the size of the process. This multiplication by Lt of s times e to the minus Lt of s is just scaling, and then we're multiplying by this indicator so that we're only taking into account the particles that are below Lt of s. Now it turns out that these processes zt are going to converge to a limit as t tends to infinity, and the limit process is going to be a process with jumps. So the particles that stay below the right boundary are going to behave in a fairly predictable deterministic way. We can see that from the second moment calculations. However, there will be times when particles hit the right boundary, and at those times we're going to see the process make some random jumps. So what happens at these times is that when one of these particles drifts unusually far to the right, a large number of descendants of this particle will survive because they're able to avoid being killed at 0. And this can lead to a rapid increase in the total number of particles in the process, where a substantial fraction of the particles could be descended from the one particle that drifted unusually far to the right. And that ends up showing up as a jump in the limit. Now, the size of the jump that occurs is going to be roughly proportional to the random variable w that we had on the previous slide. And from our result on the tail behavior of w, we can see that jumps of size greater than x are going to occur at a rate proportional to 1 over x. Also, the jump rate is going to be roughly proportional to the rate at which particles hit the right boundary, which in turn will be approximately proportional to the size of the process at time s. And by putting together these two observations, we can see that the limit process should be a so-called continuous state branching process. So a continuous state branching process is a Markov process taking its values in the non-negative real numbers. We think of x of t as being the size of a population at time t. And the transition functions for this process need to satisfy this branching property. And this is saying that we get the same distribution starting from a population of size a plus b and running the process for time t as what we get from running two independent copies of the process for time t, one started from a and one started from b, and adding them together. And in fact, Lamperti showed that continuous state branching processes are precisely the processes that arise as scaling limits of Galton-Watson processes. Now, Lamperti also gave another useful characterization of continuous state branching processes. So let's let y be a Lévy process with no negative jumps, which starts at some positive value and is stopped when it hits the origin. And then this process x that we get by time changing a Lévy process is a continuous state branching process, and conversely, every continuous state branching process can be obtained by time changing a Lévy process. And this should make sense because individuals in the population are behaving independently of one another. The continuous state branching process should be behaving like a Lévy process with stationary independent increments, except that when the population size doubles, changes in the population are going to occur twice as fast, so we need to have this time change to make the time run at a speed proportional to the population size. Now, because y is a Lévy process, the expected value of e to the minus q times y of t can be written in the usual Lévy-Hindschen form, where alpha is a drift, beta is the variance of a Gaussian component, and nu is a Lévy measure which governs the jump rates of the process. And this function psi is known as the branching mechanism of the continuous state branching process. Now, in 1992, Neveu studied a continuous state branching process whose branching mechanism is given by A times Q plus B times Q log Q, which can be written this way in Lévy-Hintgen form. And from the form of the Lévy measure, we can see that jumps of size x are happening at a rate proportional to x to the minus 2, and therefore integrating, we see that jumps of size at least x are occurring at a rate proportional to x to the minus 1. And that's exactly the behavior that we saw for branching Brownian motion. So that leads to the following theorem. We'll assume that zt of 0, that's our measure of the size of the process at time 0, converges in distribution to some limiting random variable z. And we'll assume that Lt of 0 minus R of 0 is converging in probability to infinity. So this is saying that the rightmost particle does not start out too close to the right boundary at Lt of 0. And then as t goes to infinity, the finite dimensional distributions of these processes zt are converging as t goes to infinity to the finite dimensional distributions of a continuous state branching process with branching mechanism A times Q plus 2/3 Q log Q, where A is some constant whose value we actually don't know. Notice also here that there is a time change which maps the time interval from 0 to t onto the positive real line. And so behavior of the branching Brownian motion near time t is corresponding to behavior of the continuous state branching process at very large times. And I should mention also that convergence of branching Brownian motion to Neveu's continuous state branching process was established in earlier work with joint work with the two barystickis in the case where we had a slightly supercritical drift. What's new here is establishing the result in the case of critical drift, which leads to this slightly more complicated time change. So because of this connection, it will be useful to review some asymptotic results for continuous state branching processes. So let's let capital X be a continuous state branching process started at the value little x and with branching mechanism A times Q plus 2/3 Q log Q. Now some early results due to Gray tell us that this continuous state branching process does not go extinct and does not explode in finite time. And so with probability 1, x of u is strictly between 0 and infinity for all positive times u. Furthermore, one can show that if we let alpha be e to the minus 3a over 2, then this continuous state branching process tends to infinity with probability 1 minus e to the minus alpha times x, and tends to 0 with probability e to the minus alpha times x. And the way we think about this result is that the continuous state branching process at time 0 may include a certain number of so-called prolific individuals whose number of descendants at time u will tend to infinity as u tends to infinity. And it turns out that the number of such prolific individuals has a Poisson distribution with a mean of alpha times x, and that leads to these two probabilities. And because of the theorem on the previous slide, survival of the branching Brownian motion until time t roughly corresponds to the event that this continuous state branching process is tending to infinity as u tends to infinity. So we're now ready to state the main result about the survival probability for critical branching Brownian motion. So for simplicity, we're going to assume that the initial configuration of particles is deterministic, but it may depend on t, and recall that zeta denotes the extinction time. So let's suppose that zt of 0, that's our measure of the size of the process at time 0, is converging to z, and we'll also assume that the position of the rightmost particle is at time 0 is not too close to the right boundary. And then the limit as t goes to infinity of the probability that the process survives for at least time t is 1 minus e to the minus alpha times z. That's coming from the result for the continuous state branching process. Now, if zt of z is tending to 0, and the position of the rightmost particle is not too close to LT of 0, then the probability that the process survives for at least time t is converging to 0. More precisely, we can approximate 1 minus e to the alpha z by alpha times z to get the result that the probability of survival until time t is asymptotically equivalent to alpha times zt of 0, where again this symbol here means that the ratio of the two sides tends to 1 as t tends to infinity. Now, a special case of this result is when the initial configuration consists of just a single particle at x. That's the result that was presented at the beginning of the talk, and then we get that the probability that the process survives for at least time t from the formula for zt of 0 is asymptotically equivalent to alpha times pi times x times e to the x minus lt of 0. At the beginning of the talk, we stated this result with an arbitrary constant c in front here, but this is really the same thing because alpha depends on the unknown constant a from the continuous state branching process. So we really don't know the value of that constant. Finally, one could consider the case where at time 0 there is a single particle at the location lt of 0 plus x, and then we fix x and let t tend to infinity, and then the probability that the process survives for at least time t is converging to phi of x, where phi of x tends to 1 as x tends to plus infinity, and phi of x tends to 0 as x tends to minus infinity. We don't have an explicit expression for the function phi, but we know that it satisfies a certain second-order differential equation, which is related to the FKPP equation. Now, as a corollary of this result, we can get an asymptotic result for the survival time of the process, conditional on the event that the process survives for an unusually large time t. So we'll assume, as before, that zt of 0 tends to 0, so that survival until time t is unlikely, and the position of the rightmost particle stays away from the right boundary at time 0. And so then this result says that conditional on survival until time t, the amount of time past time t for which the process survives is of the order t to the 2/3 power. And more precisely, t to the minus 2/3 times zeta minus t is converging in distribution to an exponential random variable. And the proof of this result is sufficiently simple that I decided to sketch it here. We can simply compute the probability that the process survives for at least time t plus yt to the 2/3, conditional on the event that it survives for at least time t. We can write this conditional probability as the ratio of these two probabilities. And then from the result on the previous slide, the numerator is asymptotically alpha times z sub t plus yt to the 2/3 of 0, and the denominator is asymptotically alpha times zt of 0. And so then it's just a matter of writing down the formula for zt and doing some asymptotics to see that this is asymptotically equivalent to e to the minus cy over 3. And that's where the exponential random variable with a mean of 3 over c is coming from. So now we're ready to state our Yaglom-type limit theorem for the configuration of particles at time t, conditional on the event that the process survives for an unusually large time t. And so the key idea here is that we want to think about the question of what would the configuration of particles have to look like at time t in order for the process to survive until approximately time t plus s. Well, first of all, z sub t plus s of t shouldn't be too small or too large. If z sub t plus s of t is close to 0, then the process will most likely go extinct before time t plus s. On the other hand, if z sub t plus s of t is very large, then the process will most likely survive well past time t plus s. So z sub t plus s of t should be roughly of order 1. Now also, this process should have had enough time for the particles to settle into a sort of stable configuration. And so from our results on the density of branching Brownian motion in a strip, we see that the density of particles near y should be roughly proportional to e to the minus y times the sine of pi y over L sub t plus s of t. And in particular, we see from this that the rightmost particle should be reasonably close to L sub t plus s of t, which is c times s to the 1/3 power. And also, a fairly short calculation tells us that we have to put down approximately this many particles according to this density in order to make z sub t plus s of t be order 1. And as a result, we see that the log of the number of particles at time t should also be approximately c times s to the 1/3 power. Now we know from the previous slide that conditional on the event that we survive until time t, the amount of additional time past time t for which the process survives should be approximately t to the 2/3 times v, where v has an exponential distribution. So therefore, plugging in t to the 2/3 times v in place of s, we can see that both the position of the rightmost particle at time t and the log of the number of particles at time t should behave approximately like c times t to the 2/3 v to the 1/3 power, which is c times t to the 2/9 times v to the 1/3 power. And so that can be formalized in this theorem here. We assume again that the initial configuration satisfies the condition that zt of 0 is going to 0 and that no particle starts out too close to the right boundary. And then if we condition on the unlikely event of survival until time t, both t to the 2/9 times the log of the number of particles at time t and t to the 2/9 times the position of the rightmost particle at time t are converging in distribution to the cube root of an exponential random variable. Finally, one can ask, if we condition on the event that the process survives for at least time t, what can we say about the behavior of the branching Brownian motion before time t? And so we have this theorem here. We make the same two assumptions on the initial configuration, and then conditional on survival until time t, the finite dimensional distributions of the processes zt are converging as t tends to infinity to the finite dimensional distributions of a continuous state branching process started at 0 and conditioned to go to infinity. Now there's the question of what this means, because if a continuous state branching process starts at 0, then it stays there. But what we can do is start the continuous state branching process from some arbitrary positive number x and condition it to go to infinity, and those processes have a limit in law as x goes down to 0. And we can interpret that limit as the process that keeps track of the number of descendants of a single prolific individual at time 0. And that's what the limit process is here. And I'll stop there. Thank you.
Questions or comments?
So I have questions, but maybe I will also talk to you later because I'm curious to know some details.
Mm-hmm.
But one question is, if you have convergence to the Neveu CSVP process, yes, you're also able to say something about the genealogy of particles, those that survived?
Yeah, we could certainly show that the genealogy of particles converges to the Bolthausen-Snittmann coalescent. I mean, we aren't really planning to do that because it's been done in other settings, and it's more or less clear that it could be done, but yes, that could be done.
Questions, we may thank them again.